All right, let's go ahead and get started. So what we're going to do now is we're going to move to chapter 4, and that's going to be dealing with exponential and logarithmic functions. And section 4.1 is going to be on exponential functions specifically.
When is our exam supposed to be? And it's our last one before the final, right?
It'll be the last day of class basically.
Wait, so this one is the final, or
No, it'll there's going to be a chapter 4 one, and then and then technically there's going to be a final during finals week. So sometime, whenever, let me see my phone, the calculator or the calendar here, the 8th is the last day of the week, and that's a Friday. So probably on the 7th, we can have an exam if we get through everything. Now that's a key. If we don't get through everything, then we might move the final to the chapter 4 exam to the final. And so it's just going to be kind of a matter of where we are, what we're doing, how things work out. So
okay?
and and that's kind of just going to be fly by the seat of our pants to see where things are and things like that. But I think with this chapter, we only have to cover 7 sections. So in theory, we could cover 7 sections and the next day have an exam. But if we're going to actually do it that way, that's going to kind of be wait and see how it is. I think maybe at this time it really might be the final is this chapter exam. And so then basically we'd have class clear through the 7th, and then the following week we would do our final. I'd have to look at the final day, or we'd have to decide on what day we want to do it from there. So
Okay.
okay. All right, so what we're going to do is we're going to first kind of like define exponential functions, kind of look at them in a general sense, and then move on to actually, doing a lot more details. So when we have a percent change, that basically refers to a change based on some percent of the original value. So, we're going to go up by 10%, and what that ends up being is it's kind of a linear function, because maybe this would be like a 200%, but it's going to be some percent times some value, and we've moved up. And so you're going to get some kind of a linear function. Then what happens is if we have an exponential growth, we're going to have an increase based on some constant multiplicative rate. So it's not going to be just, multiplying. We're going to have some multiplicative rate. In this case, it's a 2 raised to some power x. And that's depending on what the x is going to be what you're raising the power. So, when we have 0, and then it's going to be at a 2 or whatever, it's going to keep going up, and it's just going to keep going up and up, and that's why it's called exponential, because as you can see, it just all of a sudden just starts shooting almost straight up is what happens. And then exponential decay, I didn't put that on this one, but basically it would start here and then it would go down, and basically you're doing again another multiplicative rate of change over some equal increment of time, and it decreases from the original amount over time. So it's going to go down continuously. And so these are the kind of the pictures of the increase or the growth and a linear function. So let's get a little bit more specific. And here, this one, I actually put the decay as well as the growth. And that's why I didn't put it on the previous one, because I didn't have as much space. And so this one I had more space. I could put it on the whole thing. And so let's kind of look at the behavior of the exponential function. Now, when we do the exponential function, it's basically of the form f of x equals
You cut out and we can't hear you if you're talking.
and then we have our b here is equal to 2 raised to some power x. And so a being 1, we're going to go up. We're going to have an increase. Now b, or a being negative, what happens is we're getting this decay. It's dropping down. It's negative. And so what we can say is on all of these, the domain is going to be basically all real numbers. So we can go from, negative infinity all the way to positive infinity, and we're good. Now, what about our range? Well, if a is greater than 0, if we're doing the top ones, basically, it's going to go from 0 to positive infinity. Now, it doesn't include 0. It gets very, very close. So no matter how far out you go to the negative infinity, it's never going to hit 0, but it's going to get really, really close. And then it's going to go, jump up and just keep going up to positive infinity as you go that direction. Now, if a is less than 0, though, what's going to happen is you're going to go from basically a negative infinity all the way up to getting close to 0, but not including it. So we're going from the bottom up in this case. And so again, we're not going to include 0 because we never actually touch that 0. We just get really close. Then we have the in functions, as x approaches positive infinity, if we have a greater than 0, so as x approaches positive infinity, we're going to go this way. So if it's greater than 0 for a, then we're going to go up to positive infinity. But if a is negative, then we're going to go down to negative infinity. And so those are the two things there. And as x approaches negative infinity, as we go this direction, we're going to get f of x approaches 0. And if we're going with a negative, it's going to approach 0 from the bottom. And if a is positive, it's going to approach 0 from the top. So that's going to be how that works. Now, f of x is always increasing from left to right when we're going from the negative infinity to positive infinity for a greater than 0. And we're always going to be decreasing as we go from left to right when a is less than 0. Now, again, that's never going to touch the 0 x-axis because basically any base raised to an exponent never has a result of 0. So we'll never get to 0, but we'll get very, very, very close. And because of that, we have that horizontal asymptote that at y is equal to 0 because of it never touches the 0. Now our y-intercept is going to be 0 comma a. So, this one here, it's equal to 1. Well, that's what our a is. Here, this one is, it's 0, negative 1, and that's because our a here is negative 1. And so those are all the pieces we can kind of get off of the chart just in a general form. And I could have just put, a times b to the x, and this could be negative a times b to the x, and it would be the same thing. It wouldn't matter. And then wherever it crossed, that would be what your a was. Okay. So let's think about what one of these functions here is actually an exponential function and what are the others. So if we look at the first one, we see we have an x squared, an x, and a 1. And we've been dealing with these before. And what is that? Well, that's a quadratic. Okay, so it's not exponential, it's just a plain old quadratic. Now if we go to this one, we have some base raised to a power x, and so this one is exponential. And here, basically, we have a is equal to 1 because we can have that 1 out front. Then we have our b is equal to 0.875, and then it's all raised to that x power. Now our next one, well, that looks like y equals mx plus b. So, well, that's just a linear function. Okay, so that's not exponential. And then our final one here, that one's also exponential. And it's, this is our b. Now here we're raising it to the power negative 2x, and so that's a slight bit different than, just raising it to power x. But again, it's raised to something, and that's going to be the key here. So that's, the b raised to that power, and so that's why this one is still exponential. All right, so when we evaluate functions, sometimes they'll say, hey, here's f of x equals blah, blah, blah. And we have to evaluate it for, f of 3, f of 2. We have the two different examples here. And so what do? Well, we just plug in 3 into this thing. And so we have 8 times 1.2 times 3 minus 5. And what we really need to do is be sure to follow order of operations. So on our calculators, it's best just to type in type it in as we see it here on the screen. And so when we do that, what I'm going to do is I'm going to go over to our calculator and type it in as we see it there. So what we had was we had 8, and then we had a parenthesis, then we had a 1.2, and another parenthesis, raised to the power, and now we had a difference, a 3 minus a 5 in parentheses, and that should give us our answer. So it's 5.555555, and then they rounded that last one up to a 6. Okay. So what did it ask for? It asked for to 4 decimal places. What is that equal to? Well, that was equal to 5.555, and then we always kept going fives, and so that last one would be raised up to a 6. Okay. Now this one here, basically what we're doing is we're plugging in a 2 here. So that's going to be a negative 3 over 2, parenthesis 3, to the negative 2 plus 3 over 2. Okay, and so that's what we're going to plug into our calculator this time. And so if we go back to our calculator, and a lot of this stuff in this section is calculator based. So we'll have a negative 3 divided by 2. And then that was a 3, parenthesis, raised to the power. And we had a negative 2. And then we have to get down from there, otherwise we don't get it right. Then plus 3 divided by 2. And that should give us our answer here. So it's basically 1 and 1/3. And so if we do that to 4 decimal places, that gives us 1.3333, because that last 3 doesn't round this up, and so that would be to 4 decimal places. And so that's all we have to do. Again, just basically type it as it's written, and then you should be okay. Don't do any piecemeal or anything. Just do it straight in one line and then hit enter, and you should get your correct answer at that point in time. All right, so this is kind of talking about each of the pieces. So the function basically grows by a rate proportional to the amount present. So whatever we had initially, then it's going to keep growing at a higher rate each time we move up, because it's going to base the next one on the previous, and it just keeps going and going. And so that's why it's exponential. So for any real number x and any positive real numbers a and b, again, remember a and b can't be 0 and b can't be equal to 1. Then this is our growth function. F of x equals ab to the x, where a, again, is their initial value, the starting value of the function. So there, you'll see some different ones. We'll have a lot of examples today. And b, that's going to be our growth factor or growth multiplier. So if we have two functions that we're looking at, and a is going to be the initial value, so depending on what a was, they could be totally different, but it's really depending on that growth factor. So if one of the growth factors is larger than the other one, it's going to end up having a steeper curve. Now what happens, one might go up like that, and the other one might take a little while, but then what'll happen sometimes is it'll just take off. And so, there's a point where the first function it might always be greater, but then there's that point where it switches. And the one with the higher growth factor, the higher B, is going to take over, and it's going to go up higher and have a larger number than the other one at a certain point. So there's going to be a point where the higher growth factor takes over and wins the race of growing more exponential. All right, so there's a lot of example problems in this section. So here it says the population of China was about 1.39 billion in the year 2013, with an annual growth rate of about 0.6%. The situation is represented by the growth function, and they give that to us. The P of t is equal to 1.39 times 1.006 raised to the power of t, where t is the number of years since 2013. So they want to say, to the nearest thousandth, what will be the population of China for the year 2031? Okay, so notice that here, the year 2013, that was our t of 0, and we had 1.39 billion people. Okay, now we can kind of plug that into our formula here. A, well, that's what that is, because t of 0 means it's x is 0, and then the a is 1.39. And so that gives us this point here. Now our growth rate, we have to convert that to a decimal. So we move the decimal 2 places to the left, and it's going to be 1. You have 1 plus that because you're growing, so you have to have 1 more than that. And so then that's raised to the power t. And so that's how we get all the equation, or how they got their function from what was given. Now all we have to do is take 2031 minus 2013. And if we do that, that looks to be 18. Okay, so they want to know, what is t equals 18? What is the function? So we want to find p of 18. Well, we just plug in 1.39 times 1.006, raise that to the power 18. And so when we go back to our calculator, and again, I'm just going to switch back and forth a lot today on that. What do we have? Well, we have 1.39 times 1.00020, sorry. What? Yeah, like 3 zeros. I can't remember now. What was it? 206. All right, so go back. 2 zeros and then a 6, then parenthesis, raised to the power 18, and then enter. So it wanted it out to the thousandth place, so tenths, hundredths, thousandths, and then that'd be the 10 thousandths. So it's 1.548. All right, so we need 1.548 tenths, hundredths, thousandths, and that's going to be billions of people. So we still have to have our units in China in 2031. So that would be our answer that we're looking for. Again, rounded to the thousandth. When again, we're just worried about that prefix, the 1.548, and then we can add our, what units it is, billions of people. Okay. So again, plugging into equations and solving them. So it's nothing too complicated. It's just, can you plug it in your calculator properly? All right, so kind of like what we've been talking about, we can find the equation of an exponential function. So if we're given 2 data points, write the exponential model. So sometimes we're given 2 nice data points, sometimes we're given a little harder data points. And so if one of the data points has the form 0a, then we know that a is going to be the initial value, kind of like that 1.39 in the previous example was the initial value. That was what a is. Then we can basically just plug in a and then use the second point in here. So whatever that a was, we plug it in here. And our second point that they give us, maybe it was a 2 comma 3. Well, then we'll plug in 3 for y, and x is 2, and then we can solve for b. So that's what we're going to be doing. We're going to be solving for b. Now, if neither of the data points has the form 0 comma a, then what we have to do is we have to plug in both points. So maybe we have 1 comma 1 and then the 2 comma 3. So what we're going to get is we're going to have a system of equations. So we're going to plug in the first one, and we'll have 1 equals ab to the 1, and the other one's going to be 3 equals ab to the 2. And so we have a system of equations we have to solve. We solve it. Once we get it done, we'll end up with a and a b, and then we can write it in the form, whatever our a was, whatever our b was, raised to the power x, and that's going to be our function. Okay, so again, sometimes they're going to give it nice. We have a 0 comma a. Sometimes they give us two of them like this, and we have to actually solve the system. All right, so this is one where they give us the 0 comma a, and then the other one, and we have to actually just solve just for the one system. So here it says wolf population is growing exponentially. In 2011, 129 wolves were counted. By 2013, the population had reached 236 wolves. What 2 points can be used to derive an exponential equation modeling the system? And then we want to write the equation representing the population of n of wolves over time. So basically, we want some n of t. Okay. All right, so what are our 2 points? Well, in 2011, 129 wolves were counting. So we're going to say that's 0, 129. And then in 2013, which is just 2 years later, so that's going to be 2 comma, it was 236 wolves, 236, okay? So what do? Well, we just plug everything we know into this function formula, and we solve for what's left over. So we know that a is 129, so we can plug that in. So we get 129 B, we don't know. Now x, now this is where y and x we get from our second point. Well, y is 236, x is 2, and so now we just have to solve for b. We already have a, so we solve for b and we'll get our function easily. So what do we do here first? Well, we divide by 129. And so now we have 236 over 129 equals b squared. Well, what do we do with that? Well, we take the square root of both sides. And so b equals a positive square root of 236 over 129. Now we plug that into our calculator. And so we're going to take the square root of 236 divided by 129, enter. So we get 1.3525 or 26 if we round to that place. It doesn't really say, so we'll just say it's 1.3526. And so what is our function? Well, now we know that that's equal to a, which was 129, times b, which is 1.3526 raised to the power x. And now we can plug in any x values, whatever time we want. And I guess this would be a t, not an x in that case, since we're using t for n of t. And so we can plug any time in here and we'll know what the population of those wolves were if they continue growing exponentially as they did between 2011 and 2013. Okay. So the key here is being able to solve this equation, getting it down, getting our final b value, plugging that back into our function, and then just writing it out. All right, so what about one where we have two different numbers? So this one, they just give us two numbers. And so what are we going to do? Well, what we have to do is we have to say, okay, well, we're going to use, again, this initial function and plug it in, and we'll end up with two equations and two unknowns. We'll have 3 equals ab to the 1. And this one will have 4.5 equals ab squared. Okay. Now what do we do? Well, this one I can solve for a or I can solve for b, and I can plug it into this one very easily. So if I solve this one for a, what's that equal? Well, it's just going to divide both sides by b, so we get 3 over b. Okay. Now I can plug that into here, and I get 4.5 equals 3 over b times b squared. Well, that's pretty easy. Well, now b will cancel here. We have 1. Now, if I divide both sides by 3 or multiply by 1/3 on that side so it's easier to represent, then b basically is just 4.5 divided by 3. And so I'll go ahead and just put it out on a calculator. It's easy to do in your head, but I'll just do it here. Divided by 3 is our 1.5. Okay. So we now have b is equal to 1.5. Well, now what do you do? We plug that back in here. And so a equals 3 divided by 1.5. Well, that's just equal to 2, because 3 divided by that's going to be 2, because it's going to be move the decimal once here, move the decimal once here. 30 over 15 is just 2. Okay. So now we can write our function, and it doesn't say what units or whatever to use. So we could say it's going to be equal to a 2 times b 1.5 raised to the x. And so that would be our function given those 2 points. Now 2 points, if they're exponential in nature, is all you need to write the equation. So that's kind of a nice thing. What if we're given a graph of an exponential function? What do you do there? Well, that all depends on what the graph is giving you. So what we really want to do is identify 2 points on a graph. So first one we want to do is choose a y-intercept if at all possible, because that's going to be an easy one, because if you can, then you're going to have your 0, comma a. So that's going to be the easiest one to get if you can get one of those. And then the other one, you want to choose some other point as far apart from possible from that maybe intercept or whatever point you were able to get. And so you want 2 points as far as part possible. Then basically you're going to do the same thing we just did. If you have the 0a, then you have to plug in your other point and solve for b, and then you can get your function that way. Or if you end up with two numbers that are, not one of them is 0a, then we do what we just did on the previous one, where you just have to kind of solve it down and you get your a and your b and then you plug it back in. So it all depends on if you get that y-intercept or not. And if not, then you just do what we just did. If you do get the y-intercept, then it's easy. You just plug in the 1 point for your y and your x and solve for b, and then plug it back in and you get your answer. So let's look at this example here. What we have is we have a function. It's exponential in nature, and they are nice enough to give us that this point here is 0 comma radical 2. So that means a is equal to a radical 2. Okay. Now, if we want to point as far away as possible, then I'm going to go try to get that point there. So that looks like it's a 3 comma 4. So then I'll have the point 3 comma 4. And so then again, if we're using our f of x equals a b to the x, what does that tell me? Well, f of x is going to be 4 equals a is radical 2, and then b is what we're looking for, x is 3. So now what do? Well, we divide by the square root of 2. So now we have b cubed equals 4 over square root of 2. Now I'm going to take that to the 1/3 power, and I'll take that to the 1/3 power. And so b is equal to, now I just plug that in my calculator, and I get, and that was 4 divided by the square root of 2, and then out of that, and then in parentheses, raised to the power 1 divided by 3, and then enter. Now that's what it comes out to be. Now, if you work with square roots a lot, we would recognize that the square root of 2 is the same thing. And so basically what we've just found is b is equal to the square root of 2. So our function f of x is equal to the square root of 2, which is a, times the square root of 2, which is b, and now it's raised up to the x
Would it
power.
be wrong to write it in the decimal form if you didn't know that that was what the square root of 2 was? Because I wouldn't have known that.
Well, it's probably one of those things you should probably have it in square root of form, because if you put this out and you only go to 1.414, that's not going to be as accurate as the square root of 2. And so sometimes what's going to happen is if you have the square root of 2, you're going to take and you're going to actually calculate what it is. And so when you do it, you'll see, oh, hey, look at that. And that's kind of the key. There's not going to be a lot of them that have that special characteristic of, we're using a point that's 0 square root of 2. A lot of them are just going to be, 4.5, 4.85, 3.75. So they're only going to give us decimal forms. And so this is a special one. And so that one's kind of when you see square roots of 2 in answers or problems, always go back and see if you take the square root of that number, what does it equal, and then kind of go from there, because square roots of 2 are special and they come about a lot. And when one answer has a square root of 2, usually the other one does. And so I would say that would be what I would say is always try to see what that is. Now, other ones aren't going to always have a nice thing, 1/3 0.33333 or 2/3 0.66666. Those are going to be more recognizable. But square root of 2 is one of those key ones that we use a lot. And so I think it's one that is a legitimate one where knowing it, it's 1.41, blah, blah, blah. And then you're like, I don't know what that is. And then you just type in your calculator and it's there. And then if it matches, then you have the correct answer. Now, you could have worked this out and rationalize the denominator, done all the work there, and then when you took the 1/3, it's going to be the square root of 2 here. So if you did it longhand, it'd be easier to see that it's a square root of 2, but plugging it into your calculator, it shouldn't be a disadvantage as far as that goes. So,
And is it wrong to cube root it instead of taking it to the 1/3?
well, you could do the cube root, do the wherever the cube root is on here.
Like, is it the same answer?
Yeah, it's the same thing. That's what it is a cubed root. But see, there's no specific cube root functions here.
Mine
And
has like a x to the, like mine lets you do that. I think like it lets you I thought it did.
It might, but this
Yeah,
didn't.
mine has like an X to the square root of on my little button.
Oh, if you have that, yeah, you can do that. But this one, it's sometimes easier, I think. If you have a 3 and then you just take it to the 1/3 power, then you just know you take that to the 1/3 power. That way, those be to the first, and then whatever that is that way. That way, you don't have to have a cube root button on your calculator, and
Mm.
you know what to do. So yeah, it's the same thing as a cube
Oh,
root of that, but 1/3 power is a lot easier to type into almost every calculator. So.
okay.
All right, so now that we've done all this the hard way, we can also do this the calculator way. And so basically our calculator will do these problems for us as far as calculating it. And there's all that information there, but what I'm going to do is I'm just going to go through this example here and I'm just going to plug it in and kind of show you what you do. So our calculator, like I said, is really nice. So we go to stat. Now we need to edit. And then if you have anything in your columns, basically you go to the top and then say clear and then enter and it'll clear that column. And so, if there's a whole bunch of stuff in there, you just click on that and it clears it and you're done and you don't have to worry about it you don't have to delete them all by hand. It just clears it all at once. So now our question said we had the points 3, 75.98 and 6, 481.07. So our L1 column is going to be our X's. And so that first one was a 3. The second one was a 6. Now our Y's, the first one was 75.98. And our second one was 481.07. And so once we have this in here, we just hit like one more button and we can get to our answer. So we go back to stat. Now we have to go to calculate. And it's 0 on mine, but all you have to do is go down until you find exponential regression, and basically you just can hit 0. Now we said x's are in L1, y's in L2, and so we just say, yep, that's all good, and we just go enter, 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 and then calculate, and it gives us our answer. And so now it gives us the, f of x equals a b to the x power, and it gives us their numbers. Now, when you see things where you have a lot of zeros and a lot of nines and like this, what we can do is we can approximate it and say, okay, well, this is a is equal to 12 and b equals 1.85, and that will be good enough. We can say approximately. And a lot of times they'll tell us, we need to have it to some decimal place. This one didn't, but what we can say then is our f of x is equal to, well, not equal to, I should say approximately equal to, is approximately equal to, that was 12.000 whatever, times, and then it was 1.85, and then raised to the x power. So that would be our function, basically, we just found using those 2 points with our calculator. And again, this kind of goes through what we do, but all it is kind of what I showed you. You first put the L1, put everything in L1 for X's, L2 for Y, then you hit calculate and hit 0, and it does the exponential regression, and then it spits out exactly what you need. Now, a lot of them are really nice, and it gives you numbers like A equals 2, B equals 1.2 or something like that. So they're usually pretty nice. But this one, it gave it things that were, these are probably rounded numbers here, and because of that, we had to round the numbers here a little bit to get it so it looked nice for our function. Okay, but yeah, that's a really nice function, especially when you're doing something maybe you did, well, even that one by hand or this one by hand. We could go back in and plug all that in, and it's going to give us a equals 2, b equals 1.5. And I did that to check it just to make sure, hey, does this feature really work in our calculator? And it gave me the same answer. So it's really, really kind of cool that our calculators are so powerful they can do things like this. All right, so the thing everybody likes, compound interest on their money. And so basically you're earning interest on the original value as well as the interest you've accumulated up to that point. So depending on how often you compound it, you can compound it annually, monthly, daily, secondly, or however you want to do it. that is going to be how we're going to compound it. And so we're going to have some kind of annual percentage rate, and it's called the nominal rate. And basically, the yearly interest rate is earned by an investment account, and a nominal means it occurs some number of times per year rather than just one time. So, if we're doing, semi-annually, then it would be twice a year. If we're doing quarterly, it'd be 4 times a year. If we're doing, monthly, it's going to be 12, and so on. So you just kind of have to know what the terminology is in business to kind of know what each of those items are as far as your value for the number of times per year it's accumulating. And our overall formula is just this. So A of t equals P times 1 plus R over N raised to the NT, where P basically is going to be our starting amount, our principal we added into the account to gain interest. R is our rate as a decimal. N is the number of times a year it compounds. And then T is however many years or whatever units we're using that we want to go out from. So maybe 18 years from now, what is it going to be equal to? And then our A of T basically is going to be your account value after 18 years, compounded monthly at some interest rate when we put in P dollars. Okay, and so those are all basically the things we're going to do. And so what we're going to be able to do now is just plug all this into our calculator and get values out. So sometimes we'll have to, solve for AT. Sometimes they'll want us to solve things like R. Sometimes they'll want us to solve for T. And so we really have to be able to know how to manipulate algebraically this equation to get to what we need. All right, so this one, again, they're nice to give us a formula here. So it says an initial investment of $100,000 at 12% is compounded weekly. And because different banking systems use different ones, some use 50 weeks, some use 52, they said, okay, this one's 52 weeks in a year. What will the investment be worth after 30 years? All right, well, what do we do? Well, A of 30 is going to be equal to what we started with, $100,000. We'll multiply that by 1 plus our rate, which is 0.12 over n. Well, n is 52 because we did it 52 times over the year. And then we take our 52 times our 30. And so that's basically what we're going to type into our calculator now. And so if we do that, all right, so let's clear that. So we had the 100,000 times, then we had 1 plus R, which we had as 0.12, divided by our N, which was 52 weeks, raised to the power. Now we had N, which was 52, times the number of years, which was 30, and hit enter after that. That's going to be how much we have. So let me go back over here. And so after we plug all that in a calculator, our value, our A of t of A of 30 is going to be 3644,675.88. And again, with the money, I'm going to round it to the nearest penny basically, and so that would be my solution on that one. So again, it's not hard. All you do is you plug it into the calculator as it's written here, making sure to include all the appropriate parentheses, and you should get your correct value out for your A of 30. Now the next one does a little bit different. This one, they're saying, okay, well, what do we need to invest in the account? So this time we have to solve for P. So they tell us what A of T is, they tell us R, they tell us N, and they tell us T. So they tell us everything. And so all we have to do is we have to take A of T divided by that whole set of things here, and then we get our P out, okay? So basically, what we have is a 529 plan is a college savings plan that allows relatives to invest money to pay for a child's future college tuition tax-free. Lily wants to set up a 529 account for her granddaughter and wants the account to grow to $40,000 over 18 years. She believes the account will earn 6% compounded quarterly. To the nearest dollar, how much would she need to invest in the account now? Now, this is where I would disagree. To the nearest dollar, how much would she invest? I would always say round up to the nearest dollar, because if if it says you need, I don't know, let's say $144.21, that would round down to the nearest dollar of 144. But then if you do that over those 18 years, you're never going to get to that whatever the number it was you wanted to have, because you didn't have the extra 21 cents to start with. So most times in business things, they would actually say round that to 145, round up to the near round up it instead of round down it, and then that would be for sure get you the number of dollars that you want in that time frame. So that's the only difference. I disagree with how they want you to round your number, just because I've done a lot of the business applications, and so I would always round that one to 145, even though it's 0.21. So, but what do we have? Well, we say we want $40,000. We don't know our P. Then we have 1 plus R, which is our rate, which is 0.06. Now we're compounding quarterly, so that's going to be 4. Then we're going to have 4 times, now we have 18 years. And so basically we're going to take 40,000 divided by that whole thing there, the 1 plus 0.06 over 4 raised to the 4 times 18. So that's going to go over here as well. And so P then is going to equal, now if we plug all that in our calculator, all right, so what did we have? We had $40,000, and we're going to divide that by that whole thing in the bottom. So that's going to be a 1 plus, then we had a 6.06, and divided by quarterly, which was 4, and then raised to the power 4 times 18, and that should get us our value. So it says we should invest $13,693.20 basically, but it said round to the nearest dollar, so that would be 13,693. And if I was doing it, I would actually round it to the 694, because that way I would for sure have enough if I had to have exactly 40,000 or more. And so this was going to give us 13,693, and so that's how much you would have to invest in, time 0 to get to 18 years from now having $40,000. Okay. So again, a lot of this is plug in numbers into an equation, solve them, and you get your answer. Now, we're also going to get into things where we're working with E. So the number E represents an irrational number, and its form is 1 plus 1 over n raised to the power n, and n just keeps going on and on and on with to infinity. And basically, if you look at what E is equal to, and we think about that as E to the first, that's approximately 2.718282. Okay, so that's what it equals to, but our calculator nicely has a function called E to the x, which we can use. And so what we want to do is make sure we can use that calculator function. And so we're going to find e to the negative 0.05 and e to the pi. Okay. So what we're going to do is we're going to do both of those. And our e function is right here. It's second ln. Okay. And then we just put in our number. Well, the first one is negative 0.05, and that gives us that value. Okay. And so then, oh, what did it wanted 0.05, 0.5 or 0.05, I forget. 0.05, okay. Making sure I did the right one. And the other one that said it wanted e to the pi. So we have e, then pi is over here, and that's going to be 23.140692, and so on. And so 9512, that's probably as far as we need to go. 0.9512, and this one was 23.1407. So if we go to 4 decimal places, that would be what we need. Now, if they wanted 5 or 6, you could just continue on out, but that's basically what it is. You just plug it in your calculator and you get the value out. So nothing complicated. It's just making sure you can use your calculator for when you do things later on. Okay. All right, so with the ease, what we can do is we can do some continuous growth models, business applications, as well as things like scientific radioactive decay, things like that, or even just growth. And what we're going to use is we're going to use the base E. So that's going to be our base. And so instead of B, we're going to put a E here. And so it's going to be A, E, and to the RT. So these are going to be how they function. Now, if you do business, you know it's going to be PERT, and it's going to be P, E to the RT, where P is going to be your principal. But basically, you have your A of T is going to be your final value. A is that initial value, whatever you plugged in, $100,000 or, 100 milligrams of radioactive material or whatever. R is going to be your continuous growth rate. So depending on if you had a growth of 0.25, or if it's negative, then that's going to be a decay. So depending on if you have positive or negative here means if you have growth or decay. So positive, you get growth, negative, you get decay. And then T is just the elapsed time. So you have to make sure your units kind of match there as far as times. But that's going to be kind of the general form. Now the business form, like I said, it's just the same except it's pertinent. So P is going to be your principal instead of your A. And it's the same thing if you think about it. A is your initial value. P is your initial value invested. So they both mean the same thing. It's just a matter of lettering. And sometimes I find it easier to remember PERT because I've used it a lot over the years with business. And so that makes it so it's kind of nice to remember. And then you can just say, oh yeah, when I'm doing the regular growth or decay function, that's an A value. So it's nothing different there. Okay. And so what we're going to do is we're going to use these two functions to solve different kinds of problems. So the first one we're going to do is calculate the continuous growth. And again, this one we're going to use PERT because, we're investing something. So our A of T is equal to P times E RT. So our E to the RT. All right, so when we're investing, that's going to be our P. So that's going to be $100,000. E to the R, or our R is in decimal form, 0.12 times, well, how long did we do it for? 30 years. And this is the continuous growth, or the compounded continuously function for interest. And so now what we can do is try to get it to show. There we go. Now we're just going to plug in what we had. Well, we had $100,000 we invested initially. Now we're going to take that times E raised to the power. Now our interest rate was 0.12. Multiply that by the number of years we said, and they said they wanted 30 years. And that gives us our value. If we compound continuously for 30 years at 12% interest, that's what our value is going to be. So if we go and we write that down over here, now if we round to the nearest penny, that 4 is not going to raise that 4 up. And so this gives us the value 3659823.44. Okay. And so if we invest this much initially, compounded continuously at 12% per year for 30 years, we're going to end up with, almost $4 million, 3.5 million plus change. So quite a nice bit of change, but I'm pretty sure I can guarantee you'll not find something you get 12% interest over the whole 30-year period. It's going to be a lot lower than that, especially when you're compounded continuously. All right. What's our next one asked for? Here we got a decay rate. Okay, now decay means we're going to have a negative growth. We're not going to be gaining. So in this case, instead of having R being positive, R is going to be a negative, and its rate is this. It's going to be 0.173. So R now is a negative. Now, how much will 100 milligrams of radon decay to in a year? Well, that's our initial amount. So that's kind of our A. So that's 100. And remember, for this one, it was A of T is equal to A E to the RT. So now we have A, we have R, and we have time as a year. But remember, this is that much per day. So a year, that's 365 days. So we have to make sure we have the same units. So that's kind of a key thing to make sure your rate and your time are in the same units. And so basically what we're going to do is we're just going to plug in A of 365 equals Now we have A is 100, e to the r is negative 0.173 times, now we have the number of that's going to be 365. And now we plug this into our calculator. Let's clear that so we can kind of see a little bit better. All right, so we'll have 100, and then we'll have e to the power, and now we're going to have a negative 0.173 times the number of days in a year, and that's going to give us 3.77 times 10 to the negative 26. So that's equal to 3.77 times 10 to the negative 26. All right, so that's going to be milligrams. Now, something times 10 to the negative 26 is a very, very, very small number. So with this one, we can approximate and say, well, that's approximately 0 milligrams, because trying to measure something on a scale of any sort out to the negative 26 milligrams is going to be very much impossible. So we can roughly say that that's 0 milligrams. So when you get super, super small numbers like this one, then if we're doing a decay of some sort, then we can say that that's equal to approximately 0 milligrams. Okay. So again, the key things in this one were, we know it's a decay, so instead of being a positive 17.3, it's a negative 17.3%. It's per day, and so then our year, we have to convert that to days, and then when we plug it all in, everything's in the same units, and then we should be okay as far as how that goes. All right, so here's another one. Now this one is slightly different. You can do this one two different ways. I did it one way. Another way is using just different variables. And so here we have a scientist begins with 100 milligrams of a radioactive substance that decays exponentially. After 35 hours, 50 milligrams of the substance remains, and then they want to know how many milligrams remain after 54 hours. So what we're going to have to actually do is we're going to have to calculate what our rate is. Then we can put that back into our exponential decay function, and then we can plug in our new time and solve for how many milligrams is that way. So at time of 0, so t of 0, that's equal to 100 milligrams. So that's basically our 0, 100. Okay. Now, after 35 hours, it's 50 milligrams. So then we know 35 hours is going to be 50 milligrams. Okay. So between the two of these, I can write my equation. Now, since we've been working with exponentials for radioactive decay, I'm going to write it in the formula like this. And so I'm going to say, okay, well, if I plug in my appropriate value for y, that's 50, equals, well, my a is 100. Then I have e to the r, which I don't know, and t, well, what is t? Well, that's 35, because we know it's 35 hours later, we have the 50 milligrams. Now I need to solve this for r. Okay, so what do I do? Well, first I'm going to divide both sides by 100. So 50 divided by 100 is a half, and that's e to the r times 35. Okay, now I know if I take the log of something, the natural log of e base, then I'm going to get these to come down in front. So if I have e to the x, if I take the ln of that, then I can bring this down and I have x ln of e. Well, ln of e is just 1, and so then I just get that as x, okay? But if I do something on one side, I have to do it on the other. So what I'm going to do is I'm going to take the ln of 1/2 equals, now I'm going to know that I can bring it down over here. So that's going to be 35r times ln of e.
Wait, is this something that we should know already or
Well,
remember at least?
this is kind of logs. This is something you should maybe know. That's why I did it this way, because I knew that ln of e is 1, and so that's why I did this. This is just kind of rules of logs. So this is something that probably is going to come up a little bit later. So I'm going to show you this way, and then I'm going to show you the way um, how we could do it a different way, because we could also go back all the way to, well, somewhere back here, this function. We could do a b to the x, because it's still going to be, instead of b, we say I'm using e now, and so that's going to be kind of the key difference. And so I did it this way because I know that when I do that, then this goes to 1, then I can divide by 35, and so r is just going to be the ln of a half divided by 35, and if I do that, so it's going to be ln of 0.5 divided by the 35, and that's going to be a negative 0.0198. So that's going to be a negative 0.0198. So that's my r. And so now I know that my function now is a of t is equal to 100 e to the negative 0.0198 times t. And so now I can plug in any t. In this case, they wanted what is 54. So now
I'm not I'm not getting at all what the whole LNE, all of that was, I
yeah,
guess.
yeah, that's LNE is one of those things you probably learned in high school. That's how long ago I remembered it from. And ln of e is just equal to 1. If you plug it in your calculator, I'll kind of show you here. So anyway, what we're going to do is we're going to do a of 54. So we'll also do that while we're over there. So, and it's just a function. So if we take the ln of e to the 1, which is just e, oops, that's going to give me an error, I'm pretty sure. That's just 1. And so it's just a definition of natural log, or the log base e function is that's kind of the definition. And so
And then,
that,
but then you took ln of 1/2 and divided that by 35 to get the negative 0.0198.
well, yeah, because I knew that that was equal to 1, so that drops out. So I just have
That just makes
35
that
r.
one R.
So that just means 35r equals log of 1/2. So to solve for r, I just divided both sides by 35, and then it's just plug that in my calculator, and I get this value.
You have to take the ln of both sides when you do that. When
Yeah,
you
whenever you do something, it's just like everything. If you do one on one side, you have to do it on the other side. So I took the log on this side and I took the log of that side. And then when I did that, when you take the ln of e to the r 35, then we know based on rules of logs, I can bring that down, and that's 35r ln of e, which then I know the ln of e goes to 1, and I just have that 35r left on that side. We'll do it again with the other way, but the other way you have to you're doing powers instead. So either way, this one is what I thought of first, just because I know uh, that key step right there is the log, and you can just bring it down. So anyway, so if we plug this in, now what do we have? We had 100 times e to the negative 0.0198 times the 54 hours. So there's going to be 34.33 milligrams left over. So there's going to be 33 point, was it 33? What did I forget now? 34.32, 33. All right, so let's erase that. 34.33 milligrams left over after 54 hours. Now, the other way to do it would be, instead of base E, we could just do it like we've been doing other things. We could say 50 equals 100 times B to the R times 35. And then we can say, okay, well, divide by 100. So 1/2 equals B to the, wait, I don't want R. How do I want this now? I need R times 35. Now, how would I do this one? Now, because now it's not, I don't have the nice log function. So this one, I would have to, okay, how would I do? right, so that one we would be doing times, let me think. That's why I did the other way here.
Way on purpose, but I lost your video, Barry.
Yeah, my video disappeared. I'm trying to get it back in just a second. It's working. It does that for me sometimes. She have to go to work.
She's got bio it too.
Oh, okay. Yeah, I'll be done here really quick, hopefully, with this one, and then we can. Okay, yeah, that's. All right, so let me see if I can get this back up again. Nope. There we go. All right, so. All right, so with this one, actually with the B's and stuff, we're not going to have the R in there. We're not going to have a rate. We're going to have a different kind of function. Now I can't erase. Ha ha ha. Nice. It disappears and I do. Okay, so that's gone. That's gone. So now what I'm going to have to do is I'm going to have to convert this 1/2 equals b to the 1/35. I'm going to take that to the 1/35. Take that to the 1/35. And so then I have 1/2 to the 1/35. That gives me this value for B, 0.9804. 0.9804 is equal to B. And then what I can do is then I'll have 100 times 0.9804, and then that's going to be A of 54 equals, and then I'll raise that to the 54. And so then if I do that problem, that should get me the same 34.3 milligrams. So let's go back here. Now if I raise that to 54 times 100, whoa. Let me think about what I did here. That gives me B. So then I have B, there's that. Huh. Let me think here. Okay, so that's going to do that. And so then I will have. Should be. Maybe I'm typing it wrong here. Oh, my screen disappeared again. All right, so I'm going to have 100 times 0.9804 to the 54. Okay, yeah, there it goes. I was like, what? Why isn't it working? I must. Oh, it's times 100. I didn't put that down. That's what it was. Okay. All right, so yeah, it's 34.33. So you can do it both ways, and then you get the same answer. It just depends on, if you know the log function, or you want to do it just the old-fashioned way, the a b to the x. Okay.
On that last calculation, it would have
Mm-hmm.
rounded up to 3.34 because it was 0.338. Are we just rounding it up out to 2 decimal places?
Well, yeah, I guess if it was at 3.4 there, I just looked and saw it was because I couldn't remember. Okay, if so, yeah, so that one, I don't. This one they never actually tell us how many decimal places. So this one rounded to 3.3. This one I guess rounded to 3.4, and that's a difference again of I only took those 4 decimal places here, and those I had for here. So it depends on where your 4 decimal places are on what it does for you. So that's going to be the key difference. And so, but it shouldn't give you a wrong answer either way, because it should be able to get it within, that 100th. That would be good. So, ideally you just round it to the 10th, and then both of those would be right and be 34.3. So yeah, so that was the key thing. I just multiplied wrong when I took that. I had the times 100 up here. Okay. What I can do, Ben, since it's already so late, I'll just make some video with some extra problems and go from there, unless you want to sit and listen to me talk some more.
Oh no, I'll watch the videos if you don't mind. I mean,
All
I
right.
don't mind listening, but
Yeah. I'll just stop at that one because I didn't realize there's already 2. But yeah, when she goes, I usually know it's about time to quit. So
that's fair.
yeah.
Are we the last 2 in the class?
Not the last time I looked, but it's only 2 that showed up today, so I don't know. I'm gonna have to go, because I'll have to go look and see how many people are still here, because last time I looked, there were still 5 of us in the class. So unless they just haven't disappeared from my roster, because the 23rd was the